So this is a continuation of the screencast for week number 2 on the electric field. This is part 2. We'll go over some examples. So first, let's just recall what we had in the theory. If we have sources, charged particles for the electric field, then at every point in space there's a field vector for the electric force at that point. And if I have two equal but opposite charges, the field lines, curves always tangent to the field vectors, trace out a shape for the electric field. And the formula for the electric field at some arbitrary point x in the space is q divided by 4 pi epsilon 0, where this charge is q and this charge is negative q, x minus x1 over x minus x1 cubed. So that's the field due to this first particle. And then minus, for the second particle, which is negative, x minus x2 over x minus x2 cubed. So the field due to one single charged particle is q r hat over 4 pi epsilon 0 r squared. Or I could write that as q r vector over 4 pi epsilon 0 r cubed, where r vector is x minus xq. X is the point where I'm measuring the field. xq is the position of the source, the one charged particle. If I have many charges, then I just use the superposition principle. I'll have the sum of q x minus xi over 4 pi epsilon 0 x minus xi cubed summed over I for the number of charges in the system. So this is an example with one particle, this is an example with many particles, this is an example with two particles. And finally, the field due to an extended object, which is to say something which is not point-like. If I want to know the electric field at a point, let's say x, and I have some object spread out in space, I have a distribution of charge. And if I divide the object into many small parts, each part has a little bit of the charge, dq, then I have to add the electric fields from all those different parts. dq over 4 pi epsilon 0, x minus x prime over x minus x prime cubed, where x prime is the point inside this object where dq is located. So x prime would be a point within the object. It would be the position of this part of the charge dq. And that integral will give me the electric field at the point x, which could be outside of the object, or it could be inside the object. Just some point in the volume. All right, so that's the basic idea, and now let's see some examples. The first example is the field due to a charged rod. So we have here a rod which will have some charge, let's say Q, and some length, let's say L. And now let me find the electric field at 2 points, A and B. So A is displaced from the center of the rod by some perpendicular distance. So let's call this perpendicular distance here A. So that's the position of A. It's the position you reach by starting at the center of the rod, moving away in the perpendicular direction by a distance A. So that'll be one part of the problem. And then let's redo the calculation for another point, B, which is located somewhere on the axis of the rod. So a rod of length L is placed on the x-axis. So we'll set up a coordinate system. And it's convenient to use coordinates where the rod is on the x-axis. So a rod of length L is placed on the x-axis. It occupies the space from minus L over 2 to plus L over 2. There's minus L over 2 to plus L over 2. So the length is L. And we want to determine the electric field at 0, A0. So again, this is the xy plane. So point A has coordinates 0, A0. The x coordinate is 0, the y coordinate is A. And it's in the xy plane, so the z coordinate is 0. And then part B of the problem is to determine the electric field at a completely different point, B, which is located at coordinates A0, 0. So this distance, it's not drawn to scale, this distance is also A. Now that had better not be a point right on the rod, because that would be a singular point. So we'll say that A is larger than L over 2. So this position is L over 2. A is outside of the rod, so A will be greater than L over 2. This is not drawn to scale. Now we have this case of a charge distribution. So E at the point X, any point in here, any point, we're going to specialize to these 2 points, but for any point in here, E at X is dq over 4 pi epsilon 0, x minus x prime over x minus x prime cubed. Now, since this is a one-dimensional distribution, dq I can write as density lambda, charge per unit length, times dx. Well, I better not call it x because I've already used x to stand for a different thing. X stands for this position. That's x vector. Let me call it x prime. Well, yeah, x prime is a point in the distribution. So in fact, x prime here will be a point on the x-axis. So the coordinates of x prime are x prime 0, 0. The x coordinate of x prime is x prime. The y coordinate of x prime is 0 because it's on the x-axis. The z component is also 0. So dq is lambda dx prime. I've effectively divided the rod into tiny segments of length dx prime. And dq is lambda dx prime. So lambda is a constant. I can pull it outside the integral. Lambda divided by 4 pi epsilon 0 is a constant out in front. Then the integral dx prime. X prime starts at minus L over 2 and ends at L over 2. So it's integral minus L over 2 to L over 2 dx prime. And now I need the vector x minus x prime. Well, that'll be I hat x minus x prime plus j hat y plus k hat z. So for an arbitrary point A, I'm calculating this vector r. So it's x minus x prime in the x direction. It's y in the y direction. It's z in the z direction. So it's I hat x minus x prime plus j hat y plus k hat z, divided by the length of that vector. So that'll be x minus x prime squared plus y squared plus z squared to the 3/2 power. Oh, it's the distance cubed. The distance is the square root of x minus x prime squared plus y squared plus z squared. So this distance by the Pythagorean theorem is the square root of x minus x prime squared plus y squared plus z squared. And then I have to cube that. So then I get x minus x prime squared plus y squared plus z squared to the 3/2 power. So I hope you're taking notes, because you should be trying to follow along this calculation. You're going to do similar calculations on the log kappa problems. So take notes so that you can refer back to your notes to see an example when you come to calculation of this kind in the homework assignment. Now the charge density is dq dx prime, or dq divided by dx prime. And if the charge is uniformly distributed along the rod, then that's just the same as q divided by the length of the rod. So on any little interval, the density along that interval is the charge divided by the length of that interval. Well, if it's uniform, then that's the same as the total charge over the total length. So let's consider part A. X is the point 0, A0. Now, I think you can see from the problem, at the point A, the direction of the field will be in the y direction, because this is a positively charged object, and I'm on the midpoint of the object. Well, by symmetry, the only term that will be non-zero will be in the y direction. The only component of the electric field will be on the y direction. So Ex and Ez will be 0. What it comes down to is calculating Ey. So I have lambda over 4 pi epsilon 0, integral minus L over 2 to L over 2 dx prime. I'm looking at the y component, the j hat component. Well, in the numerator, it's y. And at this point, y is equal to a. So there's y. Now in the denominator, I have x. Well, x is 0 at this point. Minus x prime squared. So that'll be x prime squared. Plus y squared. And now y is equal to a. So plus a squared. Plus z squared, but z is 0, because a is a point in the xy plane. So the denominator here is just x prime squared plus a squared to the 3/2 power. So again, you should be taking notes, and you should make sure you understand how this reduces down to this for problem A, because you'll have to do similar things on the log kappa. Well, that's all the analysis. Now it's just a question of doing the integral. Well, there are various ways to evaluate integrals. Probably the easiest way is to use Wolfram alpha. Or you could look it up in a table of integrals. Actually, the integral we have to do here is an elementary integral. I hope you've got it written down and you're taking notes. Well, it's not so elementary. Actually, in the appendix of the textbook by Bauer and Westphal, page A7, the first integral on that page is the integral we need. Here's a little calculation using Wolfram Mathematica. We have to integrate 1 over x prime squared plus a squared to the 3/2 power with respect to x prime. And since I don't express this in terms of endpoints, this line will give me the antiderivative. So there's the antiderivative. Then I have to evaluate the antiderivative for x prime equals L over 2. That's the upper endpoint, minus the antiderivative for x prime equals minus L over 2. That's the lower endpoint. So I have to combine those two terms. And here's the final result. So the electric field at that point 0a0 is in the y direction, and it's lambda a over 4 pi epsilon 0, 1 over L over a squared, square root of a squared plus L squared over 4. Or I can clean it up a little bit. Q over 4 pi epsilon 0, 1 over a squared of a squared plus L squared over 4. So that's the answer. Now it'll be interesting to look at the limit when L goes to infinity. Remember, L was the length of the rod. We were looking at the electric field at this point. If L goes to infinity, then this finite rod becomes an infinite line of charge. Then the 1 over the square root a squared plus L squared over 4 can be approximated by just 2 over L. So I can approximate this by 2 over L when L is very large. So this could either be L goes to infinity or A goes to 0. It just depends on the relative size of L and A. Anyway, for the limit L goes to infinity, this becomes 2 divided by L. I'll have Q over L. Now Q over L is the density, lambda. And then the 2 cancels the 4 here. So for a charged line with charge density lambda, the electric field at distance a from the line is lambda over 2 pi epsilon 0 a. And that's a result that we're going to see again. We can derive that result very easily using Gauss's law. So keep this in mind or write it down in your notebook. We'll see this again. Now that was part B. That was part A. Part A was to determine the electric field at this point. Part B was to consider this point, a point on the axis of the rod at a distance A from the center of the rod. So in other words, X is A0, 0. And we want to be not in contact with the rod, which would be a singular case, A greater than L over 2. Well, you can see from the symmetry of the problem, the electric field will be in the X direction. So we just need to calculate E sub X at the point A0, 0. And it's lambda over 4 pi epsilon 0 integral minus L over 2 to L over 2 dx prime. And now the numerator is A minus X prime. Remember, it's X minus X prime. X prime goes from minus L over 2 to L over 2. So X minus X prime would be A minus X prime because X is equal to A in this part. And the denominator is just A minus X prime cubed. So this will be A minus X prime over A minus X prime squared. Now that's an elementary integral. I don't even have to use Wolfram alpha. Integral dx prime over a minus x prime squared is 1 over a minus x prime. So there's the antiderivative of the integral. Then I have to evaluate that at x prime equals L over 2 minus evaluate it at x prime equals minus L over 2. And that turns out to be lambda over 4 pi epsilon 0, 2a over a squared minus L squared over 4. So there's the answer for the electric field at the point B, to be compared to the point A. So you see, I have certain common factors. I have lambda A. Here I have lambda A. I have 4 pi epsilon 0 in the denominator. It's 4 pi epsilon 0. Here I have 1 over a squared square root of a squared plus L squared over 4. And here I have L over a squared square root of a squared minus 4. Here I have 1 over a squared minus L squared over 4. So you see, if A is equal to L over 2, in other words, if you approach the end of the rod, if A approaches L over 2, then this will be singular. So there's a singularity. Now, here are the lines, here are the electric field lines. So you can see on the midpoint of the rod, the electric field points in the y direction, or in the negative y direction below the rod. And the electric field at B points in the x direction. Those are the two cases we considered. If I wanted to consider, for example, this point, well, I'd have to redo the calculation with more complicated integrals. But, I'd be able to calculate the direction in that case. Okay, so the first example involved superposition and integration. And the second example will be using Gauss's law. So Gauss's law is this general theorem. The integral, E dot dA, is Q over epsilon 0, where this is a closed surface. So S is a closed surface, like a sphere or something. And there are charges inside the volume enclosed by S. So this is S. The left-hand side here is the flux of electric field out through the surface. So we have electric field going out through the surface. Well, it could be coming in through the surface. But if the enclosed charge is positive, there'll be an electric field flowing out through the surface. And this surface integral, the integral E dot dA, is the total amount of flux going out of the surface. And Gauss's theorem says that is equal to the total charge enclosed divided by epsilon 0. And it doesn't matter what surface you use, and it doesn't matter what the positions of the charges are, it's a general theorem. So S is any closed surface. Gauss's law says that the flux of the electric field outward through S, in other words, a measure of the amount of field flowing out of that volume enclosed, is equal to the net charge enclosed by the surface divided by the electric constant epsilon 0. That's just a general theorem. Now, what makes it useful is that for symmetric systems, you could have systems with planar symmetry or cylindrical symmetry or spherical symmetry. This result can be used, or this theorem can be used, to calculate the electric field of the system throughout the volume. And there are a bunch of examples of this in the chapter on the electric field in the textbook. I think there are probably examples of planar symmetry and cylindrical symmetry and spherical symmetry. And on the long kappa problems, you'll have examples of each of these kinds of symmetries. But let's do an example of cylindrical symmetry. Determine the electric field produced by a long charged wire. In other words, it's a charged line. We could set the coordinate system up so that the wire is on the z-axis. And since it says it's a long charged wire, I could just take the charge to be anywhere, to be spread throughout the whole z-axis. As long as I'm not going to be considering the field at the end, as long as I'm considering the field sort of in the middle, I can take the limit that the wire extends off to infinity. And that'll be a perfectly good approximation. Now, if you have a charged line, then you have complete cylindrical symmetry. There's a symmetry with respect to rotation around the z-axis. In other words, all angles around the z-axis are the same. And there's also a symmetry with respect to translation along the z-axis. As long as the wire is infinitely long, this point is just the same as this point, is just the same as this point. If you have a long wire, if it's infinitely long, this is no closer to the end than this or this. So these 3 points are all equivalent. So I have two kinds of symmetry here. I have translation invariance in the z direction, and I have rotational invariance in the direction around the z-axis. That's the azimuthal angle. By cylindrical symmetry, the electric field has to be in the rho direction. So if I considered some point here, let's put it over here. If I considered some point here, the electric field would be pointing away from the wire in all directions. In other words, it's pointing in the rho direction. So E is E rho, and the strength of the electric field can't depend on the angle around the axis because I have a cylindrical symmetry. So any point, at angle 0 or angle 90 degrees or angle 180 degrees, they're all the same. So the electric field has to be in the rho direction. So its direction is rho hat. And its magnitude can only depend on the distance from the wire. It can't depend on the z position because I have translation invariance in z. And it can't depend on the angular position because I have rotational symmetry around the axis. So the symmetry tells you the form that the electric field has to have. So no matter where I am in this space, as long as I'm not near the ends, so as long as I make the wire very long, the electric field at any of these points will have this form. That makes it possible to calculate the flux through a cylinder. So the Gaussian surface will be a cylinder. It has to be a closed surface. It has to be a closed surface, and so I'll make it a cylinder. I'll make it a cylinder with height dz. So this height of the cylinder is dz. And radius, rho. And now I look for the electric field flowing through that surface. There's no electric field flowing through the top and bottom, the ends, because the electric field points away from the wire. So it doesn't go through the ends. It just goes through the width around the side of the cylinder. And at any point on the side of the cylinder, the electric field is perpendicular to that point, perpendicular to the area at that point. So the flux will just be the electric field value times the area. And when you integrate over the whole surface, I'll just get the area of the whole surface. Now the area of a cylinder is 2 pi rho times dz. It's the circumference times the height. The height is dz, the circumference is 2 pi rho. So here's the flux. It's the electric field value times 2 pi rho dz. The only reason I was able to calculate that surface integral was because of the symmetries that I have. dA is in the direction perpendicular to the surface, and E is also in the direction perpendicular to the surface. So I just have here E times dA, and E is constant as long as I have equal distances from the z-axis. So I end up with here just E times A. It has to be E in the correct direction. It's E in the rho direction times A because of this cylindrical symmetry. So there's the flux. Now what about the charge enclosed? Well, I just enclose a certain length of the wire, a length dz, and suppose that the charge per unit length on the wire is lambda. So lambda is the density per unit length, charge per unit length. And so the amount of charge in a length dz is just lambda times dz. So there's Q enclosed. Well, this and this has to be equal. Well, this has to be equal to this divided by epsilon 0. So E rho has to be, well, the dz's cancel. I can divide both sides of the equation by 2 pi rho. So E will be lambda over 2 pi rho divided by epsilon 0. And that's the result that we got before when we did the first calculation. We calculated the electric field at the midpoint of a rod, but in the limit that the length of the rod approaches infinity, we found that the direction of the electric field was perpendicular to the rod, and the magnitude was charge per unit length over 2 pi epsilon naught rho. Rho is the perpendicular distance from the rod. So this answer is the same as I got in the first example by taking the limit L goes to infinity. All right, so again, there are some examples in the book of using Gauss's theorem with symmetric situations as a way of determining the electric field. And there'll be some examples on the log kappa homework where you have to do that. So that completes part 2 of the screencast. And now you should be ready to go try the log kappa assignment.